Hi, welcome to 8.2 Polar Coordinates and Polar Equations. So far we've got everything in the XY system, the Cartesian coordinate system, but now we're going to be talking about the polar system. The polar coordinate system, like the Cartesian coordinate system, serves as a means of locating points in a plane, so it's still a two-dimensional surface. Both systems are centered at a point O called the origin, though in polar coordinates it is sometimes referenced as the pole. So the origin is the same thing as the pole, important definition there. Starting from the origin O, a ray called the polar axis is drawn. This is usually drawn horizontally extending to the right, so it corresponds with the positive x-axis. You scroll this up so you can see what I'm talking about. So here would be the pole, or the origin, and then this would be the ray. If you choose any point P other than at the origin, the line segment OP, so here's a P, this line segment OP has a unique positive length that we will label R. Has length R as in radius. We'll then assign the measure of the angle to the variable theta. So this angle will be called theta. And that's measured counterclockwise between the polar axis, this is the polar axis, and this line segment OP. So we say point P has a polar coordinate r theta. It's r away from the pole, it's theta degrees away from the polar axis. And we label this as in radiuses, or this is one like that for the radius. 2, 3, 4, 5. Also going this way. 1, 2, 3, 4, 5. So that's the basic idea. You could put it over here too. 1, 2, 3, 4, 5. So that's your polar coordinate system. Let me just state it for this. In this case, P is located at 4. And then this mark is pi over 6. This one's pi over 4. This is pi over 3. So it's at 4 pi over 3. The angle is pi over 3. Now, I found this from another textbook. I should probably note that, which textbook, I forget which one, to do proper citation. But I'm pretty sure it's out of print now. Forming a polar coordinate system in a plane, you start with a fixed point O and call it the polar origin. From this point, draw a half line or a ray. So you start some point, draw a ray. Use your horizontal and to the right. Call this the polar axis. If P is an arbitrary point in the plane, then associate polar coordinates r theta with it as follows. So here's a P. Starting with the polar axis as the initial side of the angle, rotate the terminal side until it or the extension of it through the pole passes through the point. So if you start here, you rotate it up, and here's our theta. The theta coordinate in this angle, in r theta, is this angle in degree or radian measure. The angle theta is positive if the rotation is counterclockwise and negative if the rotation is clockwise. The r coordinate in r theta is the directed distance from the pole to the point. It is positive if measured from the pole along the terminal side, so this would be a positive r. It would be negative if it's measured the other direction. So it is negative if measured along the terminal side extended through the pole. So if you went around like this, then r is negative. Okay? There is a distinct difference between rectangular and polar coordinates for a given point. For a given point in a rectangular coordinate system, the Cartesian system we're used to, there exists exactly one set of rectangular coordinates. In a polar coordinate system, a point has infinitely many sets because, we're here, it's pi over 6 is the angle. You could also come around and make it pi over 6 plus 2 pi, or 13 pi over 6, and come around again and come around again. Okay. Plot the points given by the following polar coordinates. -5, 3 pi over 2. So I first look at the angle. The angle, and just to label this is 0, pi over 2, pi, 3 pi over 2, 2 pi. This is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And we have pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. Okay. So we're going to go to 3 pi over 2. It's coming all the way around to here. But it's -5. It's not +5. It's going to go back the negative direction, so it's back up here. 1, 2, 3, 4, 5. And this is our point A. That's at -5, comma 3 pi over 2. So it seems like it's a little backwards because we get the angle first, and then we get the radius. And B is located at -pi over 3, square root of 3. So -pi over 3 is back this way, back to this part. This is -pi over 3. And then square root of 3 is like 1.71, so we'll put it right about there. No, I did it backwards. Square root of 3, -pi over 3. Okay. Feel free to pause. And these values you do want to memorize and have those standard on all your polar graphs. Coordinate conversion. Converting from polar to Cartesian coordinates, given r theta and x, y, are defined by x equals r cosine theta and y equals r sine theta. Converting, and that's the relationship. You can get the x is going to be r cosine theta and y is r sine theta. You go the other direction, a little more work. You're given x, y. R is going to be r squared, x squared plus y squared. It's a radius, hypotenuse of a right triangle. And tangent theta is y over x, where x, of course, cannot be 0. So make note of the quadrant of the original Cartesian coordinate when converting to be sure the polar coordinate falls in the same quadrant. Partly because tangent will give you values from the fourth to the first quadrant. But it might end up in the second or the third quadrant, so you've got to be aware of that. Okay, convert the point from a polar to a Cartesian coordinate. So we have 5, 7 pi over 4. So x is going to be 5 times cosine of 7 pi over 4, which is 5 times the square root of 2 over 2. So it's 5 root 2 over 2. Y is going to be 5 times sine of 7 pi over 4, which is 5 times negative square root of 2 over 2, which is negative 5 root 2 over 2. So it's 5 root 2 over 2, comma negative 5 root 2 over 2. And for B, x is negative 2.25 times cosine of pi over 4. So that's going to be negative 2.25 times the square root of 2 over 2. A decimal for that would be negative 1.59. And y would be negative 2.25 times sine of pi over 4. That's going to be negative 2.25 times the square root of 2 over 2, which is also negative 1.59. So it's negative 1.59 comma negative 1.59. Okay, for example 3, we're going to convert the point from a Cartesian to a polar coordinate. Okay, so here's our x and our y, of course. Remember, r squared is equal to x squared plus y squared, so r squared is going to be 12 squared plus negative 1 squared. R squared is going to be 144 plus 1, which is 145. So r is the square root of 145, which is, I'll leave it like that. Okay. And tangent of theta is x, or sorry, y over x. So tangent of theta is going to be negative 1 over 12. So if I do, theta is arctangent or tangent inverse of negative 1 over 12. Theta is negative 0.08314. Well, let's talk about this. What quadrant would this fall in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, negative 1. That's the fourth quadrant. Well, this certainly does put it in the fourth quadrant then, going negative, square root of 145. So we could say the square root of 145 comma negative 0.08314. Okay, now b is going to be negative 6 square root of 3. So r is going to be, our squared is negative 6 squared plus the square root of 3 squared. So r squared is 36 plus 3. R squared is 39. So r is the square root of 39. And then tangent of theta is going to be y over x, square root of 3 over negative 6. Now, just to give us a visual here, we're right about there. Second quadrant. But tangent, when I do arctangent, it's going to produce something in the fourth quadrant. We have to make the adjustment. So theta is going to be arctangent or tangent inverse of the square root of 3 over negative 6. So the theta that's produced is negative 0.28103. And I have this in radian format, by the way. But that's down here. Negative 0.28103. We need for it to be over here. That's pi later. So we do negative 0.28103 and we add to it pi. And what do we get? .8606. So our point is located at the square root of 39, comma 2.8606. Okay. Now, example 4. I'm going to rewrite rectangular equation into polar form. We haven't had any experience with this yet. This is our first glimpse at polar, so you might be thinking, well, how do I write that as a polar? Well, what we do know, this is the equation of a circle with radius 9. We also know that x squared plus y squared equals r squared. So we can substitute the r squared there. R squared equals 81. So r must be 9. That is a polar equation. It means a circle with radius 9. It means you're graphing radius 9 the whole time. There's no angle to stop it. And the second case, y equals x. Well, recall y equals r sine theta and x equals r cosine theta. So what we're saying here is r sine theta equals r cosine theta. We can subtract r cosine theta from both sides, and we have r sine theta minus r cosine theta equals 0. So we have r sine theta minus r cosine theta equals 0. You can factor an r out, it'd be r times sine theta minus cosine theta. That's that. Okay, let's look at the next one. Now we're going to go from polar to rectangular. I'm going to scroll this up so we have more space to work. Okay. Rewrite the polar equation in a rectangular form. R equals 8 sine theta. So recall that r squared equals x squared plus y squared, so that r equals the square root of x squared plus y squared. So that means r can be replaced with the square root of x squared plus y squared. Also recall that y equals r sine theta. So that sine theta would be y divided by r. So we can write this as square root of x squared plus y squared equals 8 times y divided by r, which is 8y over r, as we saw earlier, was the square root of x squared plus y squared. So we can multiply both sides by this denominator, and we would have x squared plus y squared equals 8y. And maybe I should do that in a couple steps. Maybe we should say, okay, the square root of x squared plus y squared times the square root of x squared plus y squared equals 8 over the square root of 8y over the square root of x squared plus y squared times the square root of x squared plus y squared. These divide out. That's where we get x squared plus y squared equals 8y. I'm going to bring this up here. So that's x squared plus y squared minus 8y equals 0. X squared plus, now I'm going to complete the square, y squared minus 8y plus 16, half of negative 8 is 4, negative 4 squared 16, equals 16. X squared plus y minus 4 squared equals 16. And we have the equation of a circle. Did not expect that when I was looking back here. Okay, next one. We have r equals 2 over 1 minus cosine. I'm going to multiply by 1 minus cosine theta on both sides. So that we have 1 times r is r minus r cosine theta equals 2. Okay, what do we know from that? We know that r cosine theta is x, and we know that r is, as we saw above, the square root of x squared plus y squared. This right here is x. equals 2. I want to take this a step further. I'm going to add x to both sides. I'll just do it down here. So the square root of x squared plus y squared equals x plus 2. So the square root of x squared plus y squared is x plus 2. So x squared plus y squared equals x squared plus 4x plus 4. And if we subtract x squared, y squared equals 4x plus 4. We'll stop with that. Now, next one, rewrite the polar equation in rectangular form and sketch the graph. Well, we know that r equals the square root of x squared plus y squared, so the square root of x squared plus y squared equals 6. And if we square both sides, x squared plus y squared equals 36. That's the equation of a circle. And if I scale this at 2, 4, 6, r equals 6, we get a circle. So that kind of helps justify or helps to reinforce that r equals a certain number, gives us a circle with that radius. Okay, common polar equations and graphs. Just to be aware of these things, when you graph them in the calculator, you put your calculator on polar format. If r equals a number, you get a circle. If r equals a times cosine a number, you still get a circle that's shifted over to the right. R equals a sine theta, it's a circle shifted up. R equals a theta is just a spiral. Then we have what we call lemicons. They have this kind of either a circle in here or a divot. And they have different names like the lemicon with the inner loop, cardioid because it looks like a heart, a dimpled lemicon, a convex lemicon. I'm not going to test you on the names. Then we have roses. So these are important just to see. It's r equals a sine theta. And if it's 3 theta, a sine 3 theta, we get three leaves. A sine 2 theta, you get 4 leaves, kind of counterintuitive. A cosine 5 theta, you get 5 leaves, but a cosine 4 theta, you get 8 leaves. And finally, lemniscence, whatever, I can't really pronounce that. Looks like a figure 8 here. Okay, on to our last page. Symmetry of polar equations. An equation in r and theta is symmetric with respect to the pole if replacing r with negative r, or theta with pi, theta plus pi results in an equivalent equation. It's with the polar axis if replacing theta with negative theta results in an equivalent equation, and the line theta equals pi over 2 with replacing theta with pi minus theta results in an equivalent equation. I want to sketch a couple of graphs here. Okay. It feels a little backwards the way we do this. R is dependent upon theta, so I'm going to have my theta over here and r there. So I'm going to go with 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6 pi, and then I'll go 7 pi over 6. I want to show you what happens with this one. So I'm looking at 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi, and here's 7 pi over 6. So I put the values in the calculator, I plug these in, I'm getting 0, then 1.4, 1.7, 2, 1.7, so notice I got up to 2, now it's going down, 1.4, 1, I got messed up somewhere. I did up here. It's 0, then 1. Then 1.4, it's really 1.41, but that's good enough. 1.7, 2, 1.7, 1.4, 1, 0, negative 1. Now, I'm expecting it to overlap here as we go down that way. So 0 is at 0. If it doesn't overlap, I'll continue. 1, pi over 6 at 1. And I scaled this up here to 2. 1, 2. So here's the 1. Then I'm at 1.4 for the next one. 1.7. And then we're at, no, I'm off. 1.4 is closer to here. 1.7 is up there. And there's my 2. 1.7, 1.4, 1 here. Back to 0 at pi. 7 pi over 6 is that negative 1, so it's back up there. It starts repeating over itself. So we're getting as a circle here. That's a circle of radius 2. Okay, let's do this last one now. And you can confirm these on your graphing calculator. R equals 5 sine 3 theta. So here we'll have R that we want to find in the end. We're going to have theta, 3 theta. So if I do theta, then I do 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. That should be enough here. Because if I multiply by 3, this is still 0. This is then pi over 2. This is 3 pi over 4. This is pi. If you use this as 3 pi over 2, use this as 2 pi. If you use this as 9 pi over 4, this becomes 5 pi over 2, and then 3 pi. So plugging this in, plugging in 0, it really means 0 here, so you get 0. Plugging in pi over 6 means pi over 2, so you're going to get 5 out of this. Then 3.5, I'm only going to one decimal place. Then 0, because sine of pi is 0. Then negative 5, because sine of 3 pi over 2 is negative 1. Then 0, 3.5, 5, and then 0. So let's graph it on this. So we start out 0, 0. Go to red for this. And then pi over 2 is up here at 5. And then pi over 4, sorry, it's pi over 6. Pi over 6 is up here. Then pi over 4 is at 3.5. And then pi over 3 is at 0. So what happens is it comes up, it comes back down again. Now we go to pi over 2. Pi over 2 is seen as negative 5, so we're going to be down here at negative 5. And then 2 pi over 3 is going to be seen as 0. So essentially it comes down here and goes back up. 3 pi over 4, which is this one, is going to be seen as 3.5. 5 pi over 6 right here is going to be seen as 5. And then pi is seen as 0. So it comes up here and goes back down. So notice it's 3 theta and we have 3 leaves. We'll stop there today and we'll pick it up next time with 8.3. Thank you.